Okay. So, hello all. Thanks for joining. So, this in this session, we'll look at the week 6 content and the assignment from previous year for the same, so that it will help you carry forward towards the assignment that's due in like tomorrow or day after tomorrow or something. So, for now, we have seen that whatever questions that we are solving are almost similar to what's there in your current year's assignment, but still a few of you are not able to perform, and it's like we as TAs have been asked that to ask if you all have any certain queries that can help you solve the assignments in a probably in a way that will help you understand more about it, or you're not understanding few concepts or something like that. So feel free to let us know about the same. You can tell it's like me and the other TA. So my session is like from 6 to 8, another one's is from 7 to 9. Both of us that what are queries you face, or if you want any extra session for a particular topic, so we would do that also. If not, and if someone feels shy or something like that, then you also have the discussion forum to ask your queries on. You can leave your doubts there, and we as like the PMRF TAs as well as the course TAs will correspond to you there in itself. So the all probably the it's like the professor A Ramesh here, he'll also hold a live session that would be like 2 hours. That would be certainly towards the end of the course and one in the middle of the course. Since we're already at the 7th week, it can be probably towards the 10th week or something like that. I'm not so sure how NPTEL manages those, but yes, there would be a live session and it would be on YouTube. So I don't know if you would get a chance to interact with the professor or not. But if you want your certain queries to be answered in that session, he or she will read those prior to it, and during the session, they would certain is like they'll answer to those questions at first, and then they'll continue with what so the other questions they want to respond to. Okay. So, starting this session, I'm Jagriti, PMRFTA for the course of Data Analytics with Python. We are already at the 6th week now, and we'll be heading forward with the 7th week. I'm a research scholar at IIT Gandhinagar, and currently in my 3rd year in the discipline of Biological Sciences and Engineering. And my research field of view is on ultrasound for soft tissue characterization. So we'll just go ahead in the similar pattern that we were doing for the weeks and weeks followed. It's like we'll go through the content. I haven't made any slides this time also, just because there are a couple of formulas. So if you guys go to the actual lecture content instead of me, it's like my content, someone else's content, that will eventually confuse, and hence we all want that you to follow a similar content. So from my side, I'll help you guide through, okay, what's the theory and how to solve numericals on the same. We'll also go towards the Python numericals, is like how to implement the same there. I know it's like that's exactly the same formulas that are given there, but just to show that, okay, these things are feasible. If you do, if in this particular manner, things will run, programs will run. So that won't be an issue there. Okay, and followed by the assignment from the last year that will help you solve the assignments towards the assignment of this current year. So questions are mostly similar that we have seen so far, and the new TAs aren't changing the questions much, so that gives you an opportunity to gain your marks there if you're planning to take in certification for this particular course. Okay. So we'll look at we last week we don't look at this particular post hoc analysis, that is Tukey's test. So what does this mean? It's like when you're doing ANOVA, there is not checking for the mean differences in between all of the groups that you have. There are certain groups also which would have been significant, but they aren't, given you're taking the assumptions for the entire population instead of the total differences mean of two sample populations. So that is why we need to do multiple comparisons, that is comparisons in between groups and within the groups. So that is why for such analysis, we have this post hoc analysis. One such famous in between them is this particular Tukey's analysis. Okay. So here we'll be seeing this particular use of Tukey's test. This LSD is another method, that is least square difference method, test to identify the specific difference in between the means. Okay. So then why and how this would be useful is just because this 4 points over here, probably sometime in it's like when you're trying to do your own experiment, or if you're just focused on this particular course. So it can be like this points probably in MCQ way can be there, which might ask you that whenever you're trying to do any experiment, before doing an experiment, you need to make or formulate your design, that okay, a study design, how would you do those experiments, why this particular study design? Because let's say I didn't do my study design at first and I just started my experiment at first forward, and I'm now facing some issues. Now I didn't discuss it with my professor. Now that point is like I would be my own self who would be it's like is responsible to solve that particular problem. So I don't have anyone here and there because I didn't consult anyone before starting the experiment. Now if you do and you make a study design and plan, that will help you to improve your process lead. You'll get more and good productive outcomes from there. Variability eventually will decrease. Your design time as well as your development time will also decrease, and the cost of operation. Now whenever we are in research field, it's everything on the taxpayers money. Now we don't want that okay, you make an experiment, you design the experiment again and again, do that experiments again and again. So that is way it's also will reduce the cost of operation in that way. Okay, so these are some formal words that one I won't say that should know, but these are some formal words that one consults when they start their own experiments. Okay, so first is a conjecture. So that is a very formal word for okay defining your own original hypothesis that will motivate the experiment. Next follows your experiment, what analysis you will be doing, what things are you trying to investigate. Next is your analysis, final analysis, and then comes the conclusion. It's like you do some stats. Okay, what are the inferences from that particular stats? How is your experiment? Will you need to revise your experiment again and again, and like that? Okay, so there was one such example in the same where they were where they had this example that okay something the concentration or tensile strength of this particular bag depended on the hardwood concentration, and they said that okay, let's check that, and that would vary in between 5 to 20%. So then the engineers decided okay, let's take this four particular different concentrations, and they came up a plan to test at least 6 specimens, and they had a sample size of like 24 specimens to be tested, right? So then they made a good table out of it. So there were concentrations and number of it's like observations there. You take a total of observations, you take an average of those observations. Now, how is your experiment here? It's totally randomized and it's depending on a single factor, that's your hardwood concentration. So then what professor did is like just try and plot these. So from this particular plot, we are trying to see that okay, these vary incrementally, linearly they are varying with respect to the concentration of your hardwood, that okay, how much the tensile strength is increasing there. So with respect to percent 1, 2, 3, 4, how this particular tensile strength is increasing or decreasing. So when you do those things, it's like for a typical data for a single factor experiment would look like something like this, where you have this treatment. So where for us it was like n number of concentrations, then you have their own observation. So n number of times that you have tried is like doing the experiment. Then you take a total of it, you take an average of it, right? So be careful towards the notations over here. So y is like this, that we usually know, and average is like you have a bar on top of it. Now, when you take a total out of it, it would be y dot dot, and average out of it, so average total. So that's like this. Okay. So there are just three terms here. So if you get these terms at first would be good because it eventually will follow the same series of lines. So this is like sum of squares. So usually defined by SS. Now the sum of squares can be of error, can be of regression, can be of the total population. Okay, so here the sum of squares will define your entire population square. So what you have is like your entire treatment as well as the n number of observations. So I and j stand for both, and this is your total average. So you subtract from them and do the final sum of square. When it's for the treatment, it is only for the treatment. It won't account for any of the error that's in your experiment. And why this n is like for n number of observations that you did. So that's a total one. Then you have error sum of squares. So then you consider both of them and just subtract it from one error variable that you have over there. Okay. So I guess okay, we'll do that previously. So then how usually you do that is like now if you are assuming here that you have equal sample sizes, so your total sum of squares would be something like this. Your treatment would be only dependent on your treatment. Here you have two variables for the observation and for the treatment. Okay, so now if the sample sizes are not same, then you also have an ni variable over here. Why? Because here we assume that your entire population as well as your treatment variables are also of the same sample size. Here they weren't, hence we'll have another sample size variable. That's it. Small variation in the formula. So then they did an analysis of variance. That was ANOVA. We did last session. We saw it's like last Friday. We saw what ANOVA was and how one ANOVA works and why do we need to do ANOVA. So it's like first here we just wanted to see will they affect or not. So our alternative hypothesis, our own hypothesis here is to test that they do not affect the mean tensile. Yes, someone wanted to say something. Okay. So our hypothesis is that if the different hardwood concentrations do not affect the mean tensile strength of the paper. So we took our hypothesis that okay, if at first they are all same, then was no, they aren't. At least for one, it's not. Okay. So here they considered 1% significance, so that's like 0.01, didn't consider 95% or 5%. So then what we have, the sum of squares, like then you make a table for, you calculate it for all of the values. Now these values are from these particular variable table that came from this table here. So you got these values here, you got these values for these, you have these values also. So apply all of the values to the terms that we are requiring over here. When you do so, you'll get a total sum of squares you get for treatment, you get for error. Okay. When you get those, now this is how the ANOVA table look like, and we did last time also. So for treatment, you have your sum of square, for error you have, for total you have. Now their own degree of freedom for error would be a times n minus 1, because that's like for your total sample size minus 1 so of the total, and your total would be a n times minus 1. Now you find the mean square treatments. Mean square treatments also has it. Then the F statistics that also we saw from last semester, last session. So here, if you see the ANOVA table for the values that we computed, it's something like this. So you get the sum of squares from there. You know the degree of freedom first is your total sample size was something as 24, minus 1 is 23. Then you have total 4 different variations, so that's like 3. And this, if you subtract 23 minus 3, you get this 20 over here. Now you, if you divide this by this, you get this particular value. If you divide this by this, you get this particular value. From there, if you divide this by this, yes, this by this, you get this F statistic here. Now from there, you need to compute your p-value, that's your probability. So you go into the F table and see where this critical value lies and calculate the value for the same. If you don't want to do that, then you compute this. Okay, F statistic for 19.6, 3 is your numerator degree of freedom, 20 is your denominator degree of freedom, and you get your p-value from there. Pretty straightforward. Okay, so if any of the times you want to confirm that, okay, if your analysis is going well, if your calculations are fine or not, you just go and try and calculate if your numericals, the numerator, denominator, all those values are, is like you can cross, is like back calculate them again. Okay. So if you do wanted to do that again, so similarly, if now why we did this particular one minus, because this particular table will only give us value towards the right hand side. Now we want to see, it's like want to reject the null hypothesis within the region that's lesser than that. So we want to see for the left side of the region. So hence this one minus of that particular population, now value came out to be 4.93. What our F statistic was there is like 19.6. So hence it's like if you make a table and see here the value, so this is much far away from it. So the F value is much far away. It's like 19.6 from it. So we can reject the null hypothesis and say that, okay, they are different. At least somewhere they are different. So how and why and where. So for the same in Python also you can do is like just do F underscore one way, give all the populations, it will give you the p-value there and there itself. Okay, so how to do, it's like they have given another term. So okay, if this Excel files were given in your important data files, so you can access these files from there. So now you have different concentrations here, 5, 10, 15 and 20. These are the different libraries that you would need when you are trying to do these things. Now these two, stats models api.sm and this api.import OLS, we saw last time also that when we wanted to reset our entire data structure, we want this OLS one when we are trying to melt it essentially. And this api.sm is like to import that. So you read a particular file. Now you melt them. How will you melt them? Now I only want my values to be this all 4 values and I want them to be indexed. I'll say that index, treatment and values are the same. So my this OLS, that is nothing but ordinary least square. The value would depend on the treatment and give me the model summaries. Like I'll fit them towards this least square and see how it comes to. So now it gives me the summary like this. So how to interpret this particular summary? So now if you see, there are 3 variables here. Okay, wait. So first is your R square, adjacent R square. Next values are something your F statistic that you want and the probability against that F statistic. Then you have for each and every your variable and your concentration, they have given us the variations that, okay, how it varies. Okay, so for 5 is compared, 20 is compared, 15 is compared. Okay, so those are compared, and against them the t value is given to us, the probability is given to us, and the confidence interval, assuming a 95% confidence interval, those range are also given to us. So these much information you can get if you're getting this one. You also have the degree of freedom of the model right over here, which method you try to use when the data was generated, the population skewness, kurtosis. We saw what skewness and kurtosis was when we just started this particular live sessions. So now what you'll do is like you do ANOVA, like compare in between groups and within the groups is like how it differs, and use a type 1 model, because we are just using one way we are trying to do it. So we saw that, okay, it came, so these values are fine, residual came, mean errors came. So these are the similar values that we got from previously, and we got that, okay, this is also much less than that. So we can say that we can reject the null hypothesis here also. Okay, so when the null hypothesis is rejected here, so the essential motivation of why we want to do this post hoc analysis. So when it gets rejected, we know that some kind of treatment or level factor means are different, but it won't tell us that which particular means are here different. So for that, we need to have some methods or multiple comparisons, so that it will help us to investigate these values there. Okay. Uh, okay. Next, so one such test here is the Fisher's least significant difference method. That's the LSD one. Now from here onward, you'll need to compute the t-test statistic for all of the formulas. As like if you need to compute the 95% confidence interval, so how it followed back then. So these are just not as like some new formulas or something like that. The logic follows the same thing. The formula is the same thing. There are only slight modifications here and there. Okay, so this will compare with the null hypothesis being equal. So use a t-test statistic. So this is your actual, the predicted value minus your actual value. And now what you have is like twice of this. So why this? Because we assumed that the sample size here was same. Now if it wasn't, then it would vary there. So here, what is this particular? This is the mean square error. So here they have considered a two-sided hypothesis. Hence this would be like this, alpha by 2, and you get a degree of freedom like a into n minus 1 for the standard error that we just looked into the ANOVA table now. And here is how you compute. Okay, so then you have your t, you get this particular value, and you add a variable next to it. So plus minus of your particular is like sample mean, or your is like at which critical value you're trying to find that relation at. So then you get a range for the confidence intervals, 95% confidence interval. Okay. So if the sample sizes were different, then you'll have this 1 by ni plus 1 by nj. So here it was just like this. That is why this 2 came here. And if it wasn't, then you'll have similarly like this. Now this was initially variance. We need to have standard error there, hence the square root over here. Okay, so then similarly they have computed. So they have given all these values. You have the mean square error, you have a as 4 means, you also have n. So you can compute the degree of freedom from here. And then you have the t statistic too. So just input everything into the formula. So you have the t value, you get this particular value, you get 3 here. So now we see that if any of the pairs has a difference that will be more than this or would vary like just by this, then we say that, okay, the treatment means are different. If they aren't, then that group won't be. Okay, so how to do that? We just did the ANOVA for the first sample group, and we are looking at this similarly. Now here -1 sign is for the left hand side. We don't want for the right hand side like that. So we got this probability function at this particular. So this is for 95%. This is your degree of freedom here. You get the mean square error that is from here, this particular table. So this is your mean square error. The formula, you have the t times square root of this mean square error by your sample size. Now you get something like this. So you have 3 over here. Same value that you get. So this value and something that you computed here, hence both are same and got referred. Okay. So you have reference that, okay, these are following same manner. Now you see the difference in between your test statistics. So the mean values were given to you, right? So these values were given to us. Now you just compare all of the groups against. So what you do is like take the difference. We saw that, okay, this is greater than, this is greater than, this is greater than, this is greater than, this isn't. But this is also greater than. So all other are greater than that of this is not greater than that. So we can't reject the null hypothesis here, and we would say that, okay, the no, sorry, is like do not reject the null hypothesis, and the means are equal there for those particular groups. So that is nothing but for group 3 and group 2, the population means are same. Okay. So then how do we say that which particular group is different and by how much they are different? So for that, we have this Tukey-Kramer test for the post-hoc analysis. It will tell that the population means are significantly different. Can be done after the rejection of the equal means in ANOVA. It will help us do pairwise comparison and will also compare the absolute mean differences within a critical range. Now, what critical range is here? That is nothing but within your confidence interval. Okay. So this is how the Tukey-Kramer test is like. So this is like well known to you that, okay, if they are overlapping, their mean would be exactly within the center. So they would have the same, whereas the mu3 does not. So we say that, okay, this mu1 equals to mu2, but it's not equal to mu3. So this is how the critical range for this Tukey-Kramer test has been found. So these formulas, you don't need to remember all of these formulas. It would be just that you would be asked that, okay, which particular test does what, and probably a Python snippet for the same, that how do you compute these terms there. Remembering this all formulas is just not done, because for us also, when I did biostats, for me, my tutor made that, okay, you bring your own notes. So that was an open book exam. We brought our own notes. We also brought our class notes, and we would see the formula from there and compute it here. So it's not like that you need to remember all of these formulas for that sake. Okay. So you just need to understand that where and what to apply and how to apply. Okay. So this is the critical range. So this is the value from the range that you will be getting. This is your mean square within error, and these are your two different sample sizes there. Okay. Now here, the distribution would be within this particular C is like how number of columns that you would have, and accordingly its own degree of freedom. That degree of freedom would also vary at a respective desired level of your significance level. Okay. So the same table, same thing for what we had previously, the tensile strength of that particular bag, which depended on this hardwood concentration here. Okay. So we just compared the differences in between the means here. So you have the means here. So we have four groups here. So these is like 1, 2, 3, and 4 groups. You have 4 different groups. You compare the means of 4 different groups to each other. So that is like here. So this is your first mean, second mean, third, and fourth. Now you compare all of them with respect to your each and every each other value. So it's like you compare this to this, you compare this to this, you compare this to this. Okay. Then you again compare this to this value, compare this to this value. So how many permutations and combinations are possible there? You see those. Now we see that, okay, these values are like the differences came out to be this. Now we need to compute what the critical value would be from that particular range. So we know that how many columns we have. We have the degree of freedom with us. The desired value of significance is like something like this. So we get the Q statistic at 3.96 from the Q table. So there's also something called as Q table. That probably is not that of importance here. So how do you look at the table? It's like you have the columns, you have the degree of freedom. So you look at this particular value, the value is like 3.96. Okay. And that also depends that which particular side you're looking at. So this is like 0.05 and 0.1. So probably some part of the table is cropped in here, but you'll need to come see that, okay, for this particular significance level, I need to look at. Similar is like exactly similar how it's done for the T table or the F table. Okay. So you look at which particular side your hypothesis lies around to be. So same table, we got this particular p-value back then also. Okay. So you get the critical level. You have this mean square error width. So that is the within 1. From where do you get this? That is your this value. This is the error. You get divide by them. You know the sample size. So that is 1 by 6 plus 1 by 6. So how many number of observations that you're trying to do? So here it's same. So that's like 2 by 6. So 2 would be cancelled in here. You get 4.124. Now you need to compare that for all of these differences where it's greater than or less than that of it. So here it's a critical case, but it's greater than that of it. Here it's visually very less than that. So for this particular group, we can say that the means of the population are not different. Hence, we cannot reject the null hypothesis there. So for all other groups other than this particular group, the mean differences are different, or we can say are greater. However, for this particular 10 and 15% concentration, they aren't. Okay. So how to do in this particular Jupyter? It's just that this simple, it's like you compare, you have different libraries for the same. So you also have It's just basic English here. So you have a pairwise Tukey HSD test, and then you have a multiple comparison. So you do multiple comparison for your value and your treatment, and you do this Tukey HSD for a particular significance level. It will give you all of the limits. It will also say that, okay, here is the case where it is false. So it's not following that the mean differences are different for this particular population, that is 10 and 15. Okay. So there's another such example, I guess. Anyone has doubt over here on these particular questions that we just looked at? Because following all other, this problem is also similar to what we did previously. If not any doubts, then we can proceed ahead with the week 6 content. Any doubts? Yes, I have given mic access. If not, let me know if you have any further doubt. We'll go towards the next lecture. Okay, so what all we did for now was just multiple comparisons in between different groups where we assume that it was all random. Now, random in a way that they were continuously distributed experiments, continuously randomized. It was not based on the discrete samples of it. Okay, so now here what we want to look at is the discrete the randomized block trials of your experiments. Okay, so how do we do so? So we will estimate the components involving some random factors. We'll see a principle of blocking in here. So why? Because now we just saw that for a particular, because of some particular sample size, are all of the means for ANOVA told us that they aren't. But we need to know that which particular group is having or not having. So we need to go in much, it's like we need to dive deeper into it and need to see that which particular group is not following it. So then we did this post hoc Tukey's test. Now for the same, if at some times there might be cases where you are getting some level of significance, and but some of your groups which shouldn't be there, and because of which your population is varying, those values would also vary on that particular context. So hence, for the same, we need to have something called as blocking there. So if you block certain groups, isolate the effect of that particular factor, that something here is written as nuisance factors, then you'll see that your significance level much more increases and you would be able to define for the population itself. Okay. So this is something called as the randomized block design. So what you have over here is, it is useful when the units are much more homogeneous. If you have something as heterogeneous, then you block some particular elements and fill out of those. Okay, so why to do those is like same thing that we got. So your error would become higher. We want that the error to be very much lesser. Okay, so similarly, your S statistic is nothing but that particular regression ratio, and you have your mean square errors there. Okay. So as an if your mean square error increases, your F statistic will decrease. That will say that the variance is also higher, would also say that the experiment is involving much more error that it should not have. And your problems will start to arise, hence it would become more heterogeneous. That is why you need to do something like randomized block design. You need to block certain effects. Okay, so blocking in experimental is much more similar to stratification and sampling. What that means is that you'll make groups of different sets. It's like, okay, this particular group is following this trend, this particular group is following different sets. In between the group, the trends would remain the same. Okay. Next, so that is all randomized. So there was one such example for air traffic control test, and here they gave us that there were this 3 different groups and wanted to see that if the test is stress test is varying in between groups or not for these particular controllers. Okay, so we read the table, melted it into systems, then you have treatment and your own value, fit it. C is like do this OLS, that is nothing but ordinary least square, make a ANOVA table for the same. Now you get that your T test status, so your F test statistic says that it is 0.06. So if we are saying that the 5% hypothesis, 5% level of significance here we are following, then we say that, okay, we cannot reject the null hypothesis. Hence, we accept the null hypothesis. We may no longer reject the null hypothesis, saying that, what does that mean? That the variances in between all of these groups are similar, the system ABC. Now, there might be something that is blocking this effect. Okay, just like that is causing this effect. So let's say that, okay, we made a total of them. It's like added all of them here and here. Okay. And this is your column total following this particular way. So this is your average for these particular blocks. Okay. And this is the average of the entire thing. Hence, there are these many bars over there. Okay. So then you have the summary test. So this treatment means are something like this. That is for your all controls. So this is this, and this are all your treatment means. Divided by 6 is your sample size there. Okay. So you got your treatment means. Now you make this table again for the t-test statistic table. You have k minus 1, you have b minus 1 here for the block. So this is a new field that we have added. That is nothing but for the blocks that you have. Error similarly k minus 1 times n minus 1, and this is the total value that you will be looking at. So how do you go with the formula? So you take this ij value is like for the observation of the treatment in that particular block. So treatment in that block, this is for the jth treatment for the ith block and overall sample mean that we have. So these were the terminologies, and you compute and loop through them. So you take the term of the variables, if that is the sum of total squares. If it's like due to the treatment, then it's only for the treatment variable. Then it's for the block, so only for the block variable, and then you compute the error. So what error would be? Error is nothing but, so this total is the sum of this error, this particular thing, and the block thing. Now when you want to find the error, it's essentially the subtraction of all of them. So now you have all the values here. You find the f value, that is nothing but the ratio of your mean square regression value as well as your this mean square error value here. So you just take a ratio of this treatment value and this particular, so you get your f statistic from the f table, compute the critical value, you get your probability here. Okay, now we see that this particular probability is much lesser, or you can also see that where this critical value of f is lying around. You see again, if this is less than, so we can say that okay, we reject the null hypothesis. So from here you saw that when we did this blocking thing, we got to know that there was an issue with our original population, and there is something or some group which is causing this issue, because of which now our f statistic came as significant and we can reject the null hypothesis. Same thing that is done using Python. So you made you do and add another variable here, so block plus treatment. So it will check for a block also there. So you already gave a block. So what block is now? Block is corresponding to our this particular system A variable. So now you see that your p statistic is also much more lesser. So sorry, p value is much more lesser, and we can say that we will reject the null hypothesis here. Okay. So finally, we saw that our f value can be used for the treatment but was not on for the block. And now here it was for it a single factor, a normal workstation design, whereas this might also help to reduce this mean square error term, might also help to minimize it or remove it directly. But it's like it was, the study wasn't designed for that specific problem. Now then they gave another problem which had those particular values. So if you get a block total, you get a block average, you get treatment totals, you get treatment averages here, and then you compute it for the same. So you index all of them, you add a treatment here, you see your probability value, something like this. So you can reject it further. Then what they did is like you compute it by hand, those all variables. Okay. So I hope for now it's like you all might be thorough with this formulas, that why the sample size AB is given over here, how do we compute this particular values, how do you see in the table, index all of them. Okay. Then you get this but beautiful table. Making this table is the entire final thing. I don't know how it would be in the exam. Probably some of you can try and ask in the discussion forum that would be required to compute or find the tables, make the tables and over tables in the exam, or we would have something like numerical and Python based scripts. So if that's Python based, it would be easy for you to directly go and compute it. Okay. So then here's your ANOVA table from which you get the value. And like similarly, they have also given a Python code for the same. So I guess that's it. So you compare in between the ANOVA here and you see it's like, okay, it's much lesser. So you say that you can reject the null hypothesis there. Okay. I guess that's it for this lecture. 26th was done. Then following them, I guess other sections on this regression are much more easier. I guess, okay, we have ANOVA before it. Okay, so this is two-way ANOVA. So you're comparing in between multiple groups now. So you're want to see the effect of it, how different variations can vary there. Okay, so here it's like how different factors or variables are being accounted for the same. So those things you'd be looking at. So a factorial based design. Okay. So a factorial based design is nothing but where you are trying to compare in between simultaneous group and their conclusions is like, okay, how this particular group would be different from the another group. You're not only comparing them one by one, it's just going simultaneously. Okay. So this way. So when you're directly doing and you don't have any interaction, they would be all parallel lines. But if they do have certain elements do have, then you get a intersection in between them. So you'll get an interaction in between them. That interaction will tell you that, okay, this particular two groups have something in common and that we need to look at. Probably because of that, there is something that is causing the values, let's say, to be not so significant or different. Okay. So we have this particular samples, we get the replicate of them. Okay, so same table, you make another table that was like, will give you total averages. This would be for this factor A, then you have for factor B, similarly for factor B, make a total of all of them, you get an average of all of them. Okay, this way. So then all of the A, B, and observations that you have and would run in simultaneous order. So probably this type of examples do not require you to compute it on your hand. Python helps you to do that solving there. So this is like a very big example that is showing or advertising about the CAT exams and how CAT's algorithm is and how CAT syllabus is, what all things are there in CAT. Okay. Eventually, what our final thing of interest is this particular table. We want to see that, okay, there were three factors here, that this is factor B, this is factor A, three factors in each, and what are the numbers for the same. Okay, so then you need to compute, like, okay, they have given us two values for each here, the values are like, then you compute all of the variables. So here there were again different scores, and we need to see that what's the main factor for A, for the B, for the A and B. It's like there are different hypotheses and the questions for the same. So you get an interaction, okay, where it would be. So you need to find, so this particular table again. So we have seen this, we just keep adding it. Now we have added a mean square error here as well as an interaction here. Okay, so that this interactions degree of freedom would essentially be the multiplication of them. If it was A and this was B, this would be A times B. Okay, then you have the mean square error accordingly as well as the mean square error here. So nth observations, so sum of squares for all the populations total would be sum of all of them. Okay. This was fine. Okay. So input all of the variables there. So you get a mean of all of these variables here. You get a row total here, and then you get a column total here, and you find an average over here. Okay. Average of the entire population. So what you have is first are the means for both of the factors, factor A and factor B. Then you compute the sum square total, the sum square for factor A. It's like these are all, it's like very numerically focused, calculating, but probably it won't be there that much when you doing exam. And that finally will give you the sum square error. Something what should be there in the exam would be you need to interpret those variables or the results on your own, but not calculating them essentially. Then you get these things. Okay, so how to do it in Jupyter? You fit it. So this particular function OLS is very useful because that is allowing us to remold our data in the way that we want to look it at, and then you do an ANOVA over here. Now, why 2 is over here, can someone say? We were only doing 1 for now. It's like we were only following 1. Why 2 came here?
ANOVA.
Sorry?
For the two-way ANOVA. Get
Ha,
ready for
yes.
two-way ANOVA.
Exactly. So now we are looking at in between groups and within the group. So we are comparing simultaneous all of the groups again and again. Our design is like factorial based. So hence we have type 2 over here, and based on this our test statistic will vary. You can try and do 1 way ANOVA over here and you can see that how the variations would be. But that won't give you an exact replica how your data should be. Okay. Probably this was last for ANOVA and something interesting might start. So that was like 27, 28. Yes, regression. So what do you understand by regression? So regression is nothing but, okay, how are you seeing how your data looks like? Is it if it's say a linear regression, then it's like if it's all linearly varying. well, it's not more than linear regression, but okay, if how your coefficients are, how your particular variables are, you can say that what trend the data is following or not. Okay, so these are the things we'll look into it. So there are different empirical formulas, empirical models. Now here you assume that certain x level depends on this particular y level, and there's this relationship in between both of them. So what we did is we just plotted them. So this is, we used a reg plot. Now if you might say that okay, you're not getting, this particular thing is not running, so here SNS stands for a SNS here stands for a Seaborn library. Okay, this library has this thing that is nothing but regression plot. Okay, so you need to import this library. How they would have been imported as like this: import Seaborn as any variable that we want. So this can be SNS because here it was SNS. Okay, and this regression plot will help you fit it. So here you have x, y, you say that okay, the regression is true, and you check the variations for the same. Now you have just plotted the scatter plots of these your data points. Okay, now you might also get errors like, let's say you just gave these values here, x and y. Now these values came from our xy table, where you have defined that this is a data from that particular table that you're getting. Okay, so if you haven't defined them, and if you just say that x is certain array, y is certain array, you might need to define it as reg plot of, sorry, SNS dot reg plot of x is equals to x, comma y is equals to y, for it to consider that this particular string is having this data in it, but it's not just a variable that you are adding over there. Okay, followed by it you have a simple linear regression. So this model is like y is equals to, so can you say that which, or can all of you attempt and try to say that what is it looking like? So you have an equation of line, right? So is it resembling it in some other way?
Y is equal to mx plus c.
Exactly. So it's like mx plus c, but we also have a term of error over here. So that error will account that how our data are varying with respect to the equation that we are trying to fit it with. If we just eliminate that particular factor, we get something like this. So this is nothing but c, your intercept, this is your slope, sorry, plus this is your slope, and that's your variable that is dependent. So here this is an independent variable, x. Your value of y is a dependent variable. Now why error is like banished from this here, because we are taking an expectation. So expectation of an error that's just a constant value would be 0, hence it's not over here. Okay, so these are all the variables how you have, and you get a equation like this. So this is your intercept, this is your slope, so that was your regression, that our slope here was b, and hence we say that the slope here is positive. This is your independent variable, this is your dependent variable right here. So you should know how to interpret these terms. Okay, how you say that your slope is negative. So how do you compute a slope for something? So that's nothing but, say, let's say slope m can be computed if you have two certain set of coordinates given to you. Can be, oh sorry, I went the wrong way. So y2 minus y1 by x2 minus x1. Okay, and if it's couple of slopes again and again, you are comparing between groups, so that would vary in between, so that would be like a pool. Okay, here the line is constant, you don't see any changes in here, so that is why our slope is 0. So the gradient of slope changes are 0. Okay, so this is how a simple linear regression is like equation is being stated by. So that is like y cap is equals to b naught plus b1x. So here we will fit our particular data using the method called as least square. So what will least square do? It will try to minimize the error that we are trying to have. So this is our observed value and this is our estimated value. So we want to see that if our observed value is how different it is from the estimated value. So this thing is like when we are trying to fit these terms, we are trying to see that this error should be as minimum as possible. So hence we did a minimum of the sum of squares of the error over here. Okay. This is just the basic estimation process, how we do it. Okay, so then we just tried and wanted to see that, okay, how it goes through, and like this derivatives are just, I thought that no, were not that much of use. So okay, you take for first one, you take for second one, take for third one, similarly you add all of them, so you know how to expand the squared formula. Okay, eventually you get something like this. Now you want to see that if there are any variations or not. So you take a first differential. So when we want to compute the maxima of something, what you do is like you first find that particular critical value. That critical value would be when your derivative becomes equals to 0. When it is maxima, when your double derivative would be less than 0. Okay, so you get a maxima there. Now you get a 1 point when you compare the derivative to 0. And when you come is like and you'll get another point when you differentiate. So first we differentiated it with respect to an m variable, that was our slope. Next we differentiated with respect to the intercept, so we get another point here. So getting these 2 points, oops, where it went, content vanished. Okay, so what happened is you get these 2 points, and from the 2 points you'll be able to compare, okay, how your equation or slope is varying with. Okay, that's only was there. So this is how you can compute for your slope for the linear regression curve. So that is nothing but sum of there's no content here. Wait, let me just refresh this. Okay, it's coming, but it's not sharing. Wait, I'll reshare my screen. I am already sharing. Stop sharing. Okay. Huh. So we looked at these things. We saw the slope. We saw the estimation process. Then here, gotten another point. Why it's not loading there? Oh, yes. Oh, okay, 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 okay. After that, nothing was there. Okay, here just arrived it. And slope for the estimated regression curve was something like this. It's not allowing me to write now. Okay. Wait. Okay, well. Okay. So this is how the slope is something like this. So that's like, okay, we'll look at this particular formula in next lecture. There, 28 was the 29. Should have the formula there. Here. So we get the formula as this is your summation with respect to the x variable you get with respect to the y variable divided by all the x variables that you have. Now there's also one more way to write it, that is nothing but it would come below. It's like sum of squares in between within the groups and sum of squares in within the group. Sorry, within and in between the group. So that is like own product and cross product. So here it's like cross product of x and y. Below it is like x and x. Okay, so you can also a slope of particular some curve like this. So you get your x is nothing but your xi minus x bar whole square. So sum of squares, this is y like this, xy is in between them. So you can also write your slope, that is m, your regression coefficient as xy by xs. Your sum of error squares can also be something like, okay, error can be like yi minus this particular thing. Okay. So this is how our equation was, and this is our slope. This is also a regression coefficient, and then this was our intercept right over here. Okay, so you see and you estimate. So how you estimate is like this is your estimated value that came around, and this was your observed data point. So that is your actual data point here, and whereas this is the value that you are estimating your data point to be. So you're considering these many error for it to vary. So this is something called as an error bar. So you assume much, not you don't assume, well, it's based on your data. So you have this much error with respect to your data, and then sorry, Okay, so you have this much error with respect to your data, and with respect to that, you are estimating one single point for your observed data. So that is why you'll have something as error in there. Okay. So then there was an example. So you get something like number of TV ads and number of cars sold. So here the independent variable is this one, the dependent variable is this one. Okay. So you compute your regression curve. You got all the values. You just input the values and then do the statistics, the table that we used to do in class 10, 11, 12. Similarly, you follow all of them, you get the regression estimate curve. So you get an equation, how to do it in Jupyter, sorry, as like Python is like, okay, you plot all of them and you do something like this. So now what we had do with what we have over here is this was TV ad was an independent variable. This is our dependent variable, right? So what we'll be doing is we'll add this t as a constant variable. That constant is independent variable. So with respect to that particular variable is not varying with respect to anything. The scar sold is varying with respect to the number of ads that we would be having, right? So then we do this ordinal least square and we'll fit the model. We get the summary of the curve that we had previously. So this is how the coefficients would vary. So for constant it was 10, for TV ad it is 5. Okay. So now you'll be making it. So how it would be, so your value of variable y is like your y is nothing but your car sold would be this particular coefficient 5 times your TV ads plus your constant value that is like 10, that is your intercept. So this is your regression equation curve. Okay, so this is how you read these tables. So that is all you need to know, probably for the exam also. Okay, so there was another example for the same, and that example also had the similar values. Okay, then you compare. So okay, this particular example is something that, okay, so you've given all of these values, but you can't check for all of these values simultaneously. So you have want to have a model with you. So what they first previously do is like, so these all tests where it's regression, linear, and all of these employ some kind of learning in them. Now here you've already given that this is my observed value, this is my this particular value. So this is something called as supervised learning. Now in supervised learning, if you want to test and predict, first you'll need to have some particular set of data that will help you train your model. Next set of data that will help you test as well as validate what your particular training was on and if your model is performing well or not. So then what you do is like you compute the error in between the tested and predicted values. You get some error. You do the regression between both of them. So here they have done a regression for test, a regression for train. How they have done this particular thing is in the Colab notebooks there. Okay, so we saw that it was 0.5 for the test, it was 0.4 for the training. So our model performed well nicely because our regression coefficient increased. Not that much it increased. No, it's not actually significant, but yes, it increased and it's performing well better. So we can say, okay, 50% is something that a model is performing probably goodly. Okay. And then followed by the last lecture. So that is regression and the hypothesis in regression also, where we need to consider that how each and particular is like two groups would vary or not, or if it is following this regression, linear regression or not. Okay, so here we have when you do a fitting of something. Oh, it's not going up. Huh. So when you do fitting of something, so let's say my variable points are something like this. So they are scattered all away here, here, here. Okay. I hope it's visible. And then I want to fit it with respect to this, let's say a straight line, because since we are trying to do a linear regression here. Now this straight line is like it's accumulating the effect of all of these variables that are there. So these all points. So the straight line is accumulating for all of these points here, right? So it is giving me one exact value, probably something like y equals to mx plus c, a regression equation for all of the data point that I had here. So that is dependent on that particular slope of the equation and how the data points would be scattered. So it would accumulate with respect to them. But we can't just say that how it is, how better it's fitting it, right? So for the same, we have something called as goodness of fit matrix. Okay, now what this goodness of fit metrics are? Something called as R square, and you have something called as RMSE. So R square is your coefficient of determination that is there here. RMSE is your root mean square error. This, how high it is, the better your model fitting is. Error, how less it is, less variability in your data, better your fitting is. Okay, both of them comparing between your actual data point and your estimated data point. So they see that, okay, how difference or how much well fitting is there in between your two data points, or how much not it is, how much error is higher or lesser. Okay, then following by it, we also have something called as, we'll also see some hypothesis, and we'll construct the confidence interval for this regression parameter models. Okay, so here, so there was a certain relationship in between this total. We saw that, okay, this is for sum square of regression. This is for error. The total is sum of all of them. How you have for regression is nothing but the cross product of this, and for some of the products for XX, error is like this. And for B also, we saw previously how the formula would vary. So this is the formula for your coefficient of determination. Okay, so this is your sum of squares due to regression. Then you will also have your total. You know how to compute it. You also know how to compute this one. So your total would be from the error itself. When you know the error, when you don't know the error, you need to compute the standard error. Then you can find the error in that particular case. And your due to regression would be this particular cross product. Okay. So that is how you compute your coefficient of determination. Now, when we had this particular formulas, our coefficient of determination came to be like this. Now, when you multiply it by 100, you get something like this. So this value is very close to 100. So we usually say a coefficient of determination, or R square, greater than 80 or 85 is better, or it's we can say that, okay, there's a good correlation in between your variables, or we say that, okay, there's a strong correlation between variables. Okay. So here we say that, okay, it's very strong. It's like 88% of, not, we can't say it's very strong, but okay, they have used those words. Stats, we don't use words like that. And we say that, okay, there's a linear relationship in between both of them. For this, we'll also need to consult if our p-value is also saying that we are rejecting a null hypothesis or not. Okay, so we did the same thing here, and here also we previously saw that it gave us the R square. Now you might say that what this this particular R square is. So that's adjacent to different groups. So what we need to account is only this particular R square that we have over here. Okay. So same thing again. Okay. After R square, you have something called as the samples correlation coefficient. How correlated two different samples are. Now, when you go for okay, so here you see the sign of your B1. So this is your B1 sign. So this is your plus sign, or it can be also negative when your slope of the curve is negative, and then square root of your coefficient of determination. Now we have something called as your coefficient of determination. Your values would be like varying in between 0 and 1. So that is why it will only be limited to 1. Maximum it would be 1, not larger than that. Okay. It's not visible or what? It's late. So what you'll have for R square, I hope it's visible now. Okay, for R square, it would be like varying in between 0 to 1. It's not greater than that of it. But for this particular correlation coefficient, yes, the values are like R is in between -1 and +1, because that is following the size of your data set. So it can be -1. So it says that, okay, how it negatively it's related, how positively it's related. However, this is only the absolute value of the same. Okay. So you get the sign of it and you divide it. So this is how you usually do and compute it. Next thing. So you get an error over here. You assume that the error was 0, error was normally distributed, and the error values are independent. These are the things you need to consider. And also you need to know when you're trying to do assumptions or test of significance on them. So we're mostly about towards the end of it. So there are the two tests you would try and consider based on the sample sizes and the variances in between the sample sizes that you have. Okay. So both would be give you an estimate about the variance and variance, your variance of yours regression model. Okay. Disable mic. Okay. Then you do an estimate of your sample mean. So this is for your sample square error. So you have your mean square error. That is determined from your sum of square error divided by your degree of freedom. Why it is n minus 2, because it is something like n minus k minus 1. So you might also have k equals to 1 here. So hence it's like n minus minus 2. And this, since it's your sample variance error, if you want to compute for this deviation, it would be square root of it. Okay, so that is your sample square error. Now, if you want to find the standard error of the same, it's square root of it. Okay, so then you need to compute this particular, when testing for significance, you need to compute the standard error of significance of the estimate of the curve. So how you have it here, so that is nothing but this sample error divided by n minus 2. So how do you get this particular error? We just saw that, okay, this is y minus this particular cross product square. So at some point you'll need to compute it. If it is just something like if you're not doing in Python, you'll have to compute this all values. As and when you have all of these values, your life would be easy and you would be able to compute all of the variables. If you don't have, then you'll have to compute these eventually. So don't feel lazy and just do them and calculate for them. Okay, then how do we do the hypothesis that, okay, it is 0, the coefficient of ours, and it's non-zero. Get the t statistic similarly, what we have previously also, and you get a range of the t test statistic. Okay, this is same thing. So you get a standard error for this correlation coefficients curve. So that is your standard error divided by the dependence on that particular independent parameter. How with respect to independent parameter it is varying here. Okay, so then this is again for the two-sided curve. So you get this particular significance level. And how do you find the range for the same? So this range is here. This is how you find the range. So here is your point estimator, or is like your regression coefficient. Then you have your t-test statistic, and here is your standard error for the particular independent variable. You get this based on your significance level, you'll be able to compute for the same. Okay. Your f-test statistic is like the ratio of your regression to the mean square error here. I guess after it. Okay, how to compute it. So then similarly here, if you see your f-test statistic is giving something as like this. So compared on the critical value, you get some probability. Based on them also, for two different groups also you have your probabilities in here. You see both are less than 0.05. So you can say that we are rejecting the null hypothesis. Our regression coefficient is something that is not 0, and we get a value for our regression coefficient. Okay, so there's an effect in between both of them. So that is how everything was, and we are done with the week 6 lecture. We'll do the assignment now. If you have any doubts, let me know, or else we can go towards the assignment. Any doubts? If no further doubts, then we can go towards the assignment. Okay. I hope a good level of participation from all of you in it. Okay. Oops. I hope I'm not disconnected. Okay, I'm not disconnected. I hope my screen is visible. Is my screen visible?
Yeah.
Okay. So first question. Questions are visible, I hope. Okay. So the model developed from the sample data that is in the form of this we just did now is known as. So is it an equation, regression equation, a regression model, because we know it's not a correlation one, so that is actually eliminated, or is it a estimated regression equation? Which one? Anyone? Okay, well, so it's like an estimated regression equation. We're estimating for the value because this equation is not having an error term. So we'll say that, okay, it's an estimated regression equation. Else, it's if it would have an error term, it would have been a regression equation. Then such analysis, which of the following is not a required assumption about the error? Now we just saw it now, that what do we not consider when you are counting for error. We saw that it was normally distributed, it was independent, we saw the variance had to be same. So what is something that we don't expect over here? Just set the answer. Anyone? Okay, so we know that the expected value of the error would be 0. Here they say that it is 1, since it is nothing but a constant value. Okay, so hence it is like this first one. Okay. Then we have something like a regression analysis in sales Y in $1,000, advertising X in dollars, resulted in the following equation: Y equals to 30,000 plus 5X. Okay, so the above equation implies that, okay, how can you interpret this particular data? So when we have something called as MX plus C, you just try and plot that MX plus C. Okay, so let's say I made a line over here. Okay, now for my this line, okay, I guess the intercept was too less, but okay. This is my intercept, 30,000, this particular value. This is my Y, that is like in thousands of dollars. And this is my X, that is like in dollars. Okay, so now they are asking for every increase in $5, it's like 5,000. For every increase in a dollar, it's like $5. Every increase in a dollar, it's like 35,000. Increase in dollar, it's like $5,000. So let's see. So let's just do for $1 because $5 is only one such case, so we don't know if it would be true or not. Let's just do for this $1. So if we see for every increase, so we see that it's linearly increasing. If we see for $1, we say that, okay, for $1, it would be like something like $1,000 increase. And that thousand, sorry, for $1 would be 1,000. Now we have a coefficient of 5 over here. So for every one, it would be times 5. So that is nothing but increased by 5,000. So that is like this one. Okay, any doubt on this one? That's basically Y equals to MX plus C, only based on that. Okay. Okay. In the regression and correlation analysis, if R square is 1, then what do we say? What is the formula for R square? Anyone? We just saw on the slides so that you can see the formulas, get to know about it, and can interpret them. So it's essentially sum of squares due to regression divided by sum of squares due to 1 by total. So now if it is 1, we say that this total is equals to this regression. Okay, so hence our final answer is something like this, D1. Okay. Yeah. Now sum of squares of error can never be what? Can it be larger than the total one? Would it be smaller, or it's 1 or equal to 0? First option. No, so error can never be greater than this particular larger one. So yeah, sorry. Yes, it's asking that it can never be. So it can never be larger than the sum of squares of total. Yeah, yes, exactly. So this particular question, I guess I was trying to solve it. Okay. So for the given data, determine the R square value. So this is our miles per travel. This is our petrol consumption. So let's say this is X, this is Y. You'll have an X bar for it. You'll have an Y bar for the same. Okay. So then you can make two different columns. One can be X minus X bar. Another can be Y minus Y bar. So how would you do is like you can either use Python or you can determine it by the ratio. If you need to determine it by ratio, you can compute the R square as sum of square due to regression by the total one. So here you would compute as Sxy by Sxx. So Sxy would nothing but sum X minus X bar times Y minus Y bar by sum of X minus X bar ka whole square. Okay. If you do it like this in this particular way. If not, then you can also do something like this. I'll share my screen. So same way when what we saw in slides, okay? So uh, so if you make two independent variables, let's say miles and petrol consumption, so I just made two different arrays of them. what we had. You import your model, add constant as miles because this is our independent variable here. You add this ordinary least square for both of them. So I need to compute it and I fit the model over here. So what I get something like this. This is my regression results. So what I just want to see is this R square over here. So that is like 0.9506. Okay. Now following from the table, our next question is that when the testing of the hypothesis, when we are testing for this particular hypothesis, so what what would we do? Like, do we accept the null hypothesis or do we reject it? So to answer that, where will we look at? We'll look at this particular probability in here, or we can look at the probability of F statistic. Now here we see that it's much lesser than 0.05 that our originally acceptance was. Okay, so we can say that, okay, we'll reject the null hypothesis here because it's very less than that of it. Okay. Then following by it, our next question is that do we just determine the 95% confidence interval to test the hypothesis. So when we need to compute the 95% confidence interval, so this is our upper and lower limit over here. Okay. So for the same, this would be our 95% confidence interval. So this is all when you get the table with you. You do the Python analysis. So you can just see the table and compute all of the variables there. When you do not have these all things, what you'll need to do is compute them by hand. So how? By all the formulas that we have looked at. Okay. So something like this. So when it's like 95% confidence interval, you'll do it using the B1 times your test statistic, then times your standard error that you have with you. Okay. Okay, times your standard error here. So this B1 is nothing but your SXY by SXX, so likely this formula. And then you have your standard error as this standard error divided by the effect due to this independent variable. How do you compute this? Is based on your sum of squares error, that is based on your mean square error, but sum of square error you can also compute using this variable. So if you have previously computed this variable, then you can directly compute. If not, if you do in Python, you can directly do as model.fit and you just need to add one constant parameter there. Okay. So I hope these three questions that were in series are clear to everyone. Okay. Next question is the variance of error is same for all values of independent variable.
True, ma'am.
Yes. The variance of error for all independent values, we assume that yes, it's true. Okay. Last question. So we just saw it now only that how is possible a range of coefficient of determination. So first you can say that what is the range for R square? So we say that R square is like 0 to 1 and R coefficient of determination is like -1
Less
to
than
1.
one.
Yeah, so it can never be larger than 1 or it should be less than 1. Okay, like this. So B is your option over here. So this is all about this week's and last week answer. If you go and see this current week's assignment, you'll be able to see all of the sums are mostly similar to it. You just need to account it for different values probably there. So it's just a exact basic summary or review of what you just did now. If you solve the assignment right away, you'd be able to remember and do all of these things again. Okay. So that's it for today. If anyone has any doubts, they can stay or else. Thank you for joining and thanks.
Thank you, ma'am.
Thank you. Do you have any doubts? Okay. If not, then we'll. Thanks for joining.
Thank you, ma'am.
Thank you.